So the experiment that we are going to see today will be compensating systems. Why do you want to have a compensating system is, practically if you see, we have lot of inductor based elements. Say for example, we have lot of motors, pumps, we have lot of inductor based machines, right? So when you add more inductance to your complete system, what happens is, across an inductor, your it is CIVIL, you remember, right? Civil, if you have a capacitor, current will be leading your voltage, and if you have an inductor, voltage will be leading your current, or in the sense current will be lagging for an inductor. So when you have huge amount of inductor into your system, what happens is your current, if this is the voltage, your current will keep on lagging. So when it lags, what happens is your power factor will come into picture. For when there is no lagging, your power factor will be equal to 1, and when there is a huge amount of lagging, your power factor may tend to go to 0. What does it mean is, when your power factor tends to a very small value, it means that lot of powers are being fed back into the system, which is not a desirable one. And at the same time, there is a huge amount of storage that is taking place in some form, whether it may be across a capacitor or it may be in form of an energy. So you have to compensate this. If you have an lagging power factor, you have to compensate with the leading items. Leading items in the sense, you have to add more capacitors to it so that your power factor comes closer to 1. So in summary, what we can say is, if you have lot of systems that is adding to a lagging lagging system, then you add capacitor to it so that you compensate with it leading system. So that similarly, the otherwise, when you have we have lot of capacitor branches. Say for example, you have your mobile phones, a huge number of mobile phones. You have a UPS system in your house. So what are those things? Those are nothing but batteries. Those are nothing but a system that adds leading power factor to your system. So these leading power factors must be compensated with a lagging compensating system. So in short, if there is a lot of lagging, you add a capacitor to it. In case of if you have lot of capacitors in your system, you add inductor system to it so that you compensate your the phase difference between your voltages and currents. So this is the crux of the system here. There are multiple different types of these networks which helps into bringing back the phase difference between voltage and current back to a normal value. There are different types. We call them as compensating systems, and there are either lagging compensating system or there are leading compensating systems. And in addition to that, a combination of this is also possible. A lag lead compensating systems are also possible. So this is a very small setup that we have here, and in this particular setup you see that this is a fixed lag compensator. This is again a lag compensator with a tunable resistor here, and similarly on the other side, this is a fixed lead compensator. This is a tunable compensator here. And amplifiers can also be used as compensators, and this combination that you see here is a combination of both lag and lead compensator. When do you say that this is a lag compensator and this is a lead compensator is, in case of lag compensator, your input impedance will be very large, and your output impedance will be very small. Whereas in case of a lead compensating networks, your input impedance will be very small and your output impedance will be large. Let me correct if I have made a mistake. In case of a lead networks, your input impedance will be very small and your output impedance will be very large. In case of a lag networks, your output impedance will be very small and your input impedance will be very large. Okay, now if you look both these particular networks, which one is similar to your amplifier? The amplifier's ideal characteristics will be your input impedance will be very large and your output impedance will be very low. It means that your amplifier is a kind of a phase lead network, right? And how do you say that this input impedance is low and this input impedance is high? Is, you see here that there is a bank of capacitors here. Bank of capacitor, what will they do? They will they will add lead to your current. Okay, so any lagging network, so what is that we are going to see in this complete setup is we are going to give responses here and we are going to see responses across this. Please remember that whatever the response that we give here, based on the capacitive nature or the inductive nature of this particular system, either they add phase to it or give a phase lag to it. You might immediately ask me a question that if if your network is completely capacitive in nature, then we must add inductor to it, right? But we are having a capacitor network in parallel here. What is the reason behind this is because as you want a very large inductors, the size of your inductors will be very large. So when the size of the inductors are very large, you cannot fabricate and you cannot put it into your system. Whereas if you can replace the performance of your inductor by using a capacitor, then you save lot of space and you save lot of money also. So based on that only this compensating system works. So that is why you see that the most compensating systems are combinations of RC network. Here you have C networks in parallel, that is in parallel to your input and output here, whereas here you have C network in series, so that will make them as a lead network. Whereas in case of a lag lead networks, you see your capacitor, they will be in both in series combination as well as in parallel combination. I mean series combination in the sense series with your input and parallel with your output. That's what it means. Okay, so I mean let me again summarize. So all these lag networks, you will have a capacitor bank in parallel, right? Capacitor banks in parallel, parallel to your output terminals. Here in case of a lead networks, all your capacitors will be in series with your input. Similarly, they will be in series with your input. And amplifier is another kind of a lead network we have. Now let us, what is that we are going to do? What is that we are going to do is, we are going to give input across from our DSO here, right? So we have our DSO here and this is the input where this can be working as a function generator also, right? So this particular port will act like a function generator. You can generate whatever the kind of, I'll just show you how their inputs are. I'm just going to show you the inputs alone. Let me reset. Yeah. Okay, you see this yellow one, right? So this is our function generator which has generated a sinusoidal waveform. In case you want to change this waveform to a different waveform, then you can change it to square, right? A square waveform has been generated. And in case you want to generate a ramp, then ramp waveform is generated. And in case similarly DC noise, a sine waveform. We need a sine waveform. And next is, if you want to change the frequency, you can change your frequency to, already the frequency is selected, and I can change this to change the frequency. You see here that frequency now is 6 Hertz, and then I am increasing the frequency, right? And now it is 100 Hertz, close to 100 Hertz, and by this I can change the frequency also, right? So let me come back and yeah. This is the frequency, I mean 7 Hertz. I can change the amplitude if I want, right? So this is also possible. So this is the function generator part. So now we have given it to this input, right? And I have taken another probe on the output side. And I have connected to the input also, so that why are we seeing this is because if I don't use this, we have just fed our input here. We are not seeing. Right? In order to see this only, I have just cascaded both the inputs and outputs. So the first probe that you see here is our input probe. Now what we are going to do is, now what happens, you are giving some sinusoidal input to your input system, and there is a series resistance combination. And if I see, there is one more terminal here which I can use. If I use this, only difference that will take place is these are options that are given by the manufacturer. to change our gain actually, right? If I connect it here, then the gain will be different. If I connect it here, then it will got a different gain. So that is the only difference. Otherwise, there are a lot of terminals that are given for our own options. Now what we should do is, we must connect the capacitance to our system, right? So I'm going to add only one capacitor now. I have just added only one capacitor C1 to our system. Now let us see what happens to our output. So I am just connecting our probe here, right? And you can see here that we have, maybe let me scale it up. Yeah. And now you can see that both the waveforms are in phase, but there is a phase difference. You can see where you can closely, maybe I'll expand here. You see here that there is a small phase difference here, right? There is a small phase difference, and you can see here also the phase difference is 3.25 degrees or 18 degrees. It is keep changing, right? So there is a small phase difference. Now, why the small phase difference? Because we have used only one capacitor to it. In case I add one more capacitor to it, which means that I am adding more capacitance, right? When I add more capacitance, the phase must increase, right? Now you can see here I have added one more phase to our system. Now you see the phase difference, it is close to 4.73 or 4.6 degrees. Is the phase difference between your voltage and current, which means you are between your input and output system. So again, let me reiterate where is the application of this. This is nothing but we use this particular network for when there is a lag compensating that is required. So this is a phase lag network. So similarly, let me do the same example with a lead network also. Okay, now what is the procedure that you need to do is, you need to plot a Bode plot. You know, the Bode plot is nothing but the response between a longer range of amplitude with respect to the amplitude and frequency, right? So Bode plots will give you a better picture. So you have to change a very large range of frequencies. Where we can change a large range of frequencies is by changing the large range of frequencies, you have to tabulate what is your input frequency that you are giving, what is the input voltage that you are giving, and what is the output voltage that you are getting. Obviously, when you are increasing the frequency, they will be constant for a very long period of time. It will behave something like a low pass filter. They will be constant for a very long period of time, and after a very large frequencies, what happens is your frequency will start affecting your the capacitance of your network. So your capacitance will act like it will start behaving like an open circuit, right? So for a larger frequencies, so your output voltage will slowly come down. I will not completely perform the things, but I can tabulate. So the things that you will be tabulating will be your frequency. You will be changing your frequencies. You will be noting down what is your output voltage. Output voltage can be monitored directly from this here DSO. And then input voltage, we are giving a constant input voltage. We are not going to change it. Your output voltage will automatically change by changing your frequency. And then you will calculate what is the ratio of V0 upon Vi. Okay. And calculated value, it doesn't matter. And for a given 3 volts, input voltage of 3 volts, we are going to change the frequency from 10 Hertz to 10,000 Hertz. I'll just show you how to change the frequency now. You already know that now it is 7.6 Hertz. Okay, now I can change this. I am changing this. So whenever I change, like now it is 8 Hertz, right? Whenever I change, you need to change the parameter that you need to measure. Okay, so what is that? You want to measure peak voltage, maximum voltage. We need to measure the amplitude. Okay, so your amplitude is 3.03. Now just note down this particular value only, because I am going to change my frequency now. So let me change my frequency to a very large value and check this voltage. It is 2.97. I'm going to increase my voltage to say 100 hertz. Let me keep. Okay, for 100 hertz it has gone to 2.97. Almost it is constant. Let me go to say 600 hertz. Right, still it is constant. When I go in for 1 kilohertz, still it is constant. Go in for 500 kilohertz, still it is constant. Yeah, 1.1 megahertz, it is 3.03. And as I increase the frequency, you see that the amplitude is increasing, in fact, right? 8.4 megahertz, it is increasing to 3.6. And for 15 megahertz, it is 4.32. So it is not a low pass filter, it will be like a high pass filter. Initially, it was a constant value. So if you do a Bode plot, what happens is for a frequency ranging from 0 to say, for example, 10 megahertz of frequency, it will be 2.90 volts or something. And after 5 megahertz, it will start increasing to 4.32 megahertz. So you can see that if I further increase my frequency, it will start reducing it. So it will be like a band pass filter. Okay, so unless you perform the complete experiment, we will not be able to tell what kind of characteristics these lag networks gives you. Similarly, we will do the same experiment for a lead network also. I will do only demo for the lead network, and the other demos, whenever you are able to do it, you can come and perform the experiment. So let us go back and do the experiment for the lead network. So simple, whatever the input network, I am going to give it across the lead network here. If I want a different gain, I have to connect it to CT. So that is the only difference here. And output I will be monitoring. Right. So this is my output probe. I have connected it to my output probe. Please see here that I have not connected anything between my main network and the resistance network. So when I connect it to a resistance network, I have used only one gain. So just to show you. Yeah, frequency should be at least 50 hertz. Yeah, okay. So now you see that the phase difference is minus 87.8 degrees, close to 85 degrees, right? So which means that it is given as a lagging power factor when compared, though this is a leading network, we are compensating it with a negative phase shift. This is the phase difference between 1 and 2, which means that 1 is your input and 2 is your output. So the phase difference here is minus 87 degrees. Again, you can repeat the same experiment, that is, we can change the frequency here. So we can change the frequency. When you change the frequency, there will be a change in your phase shift. Again, you repeat the same process by tabulating what is your input frequency, what is your input frequency, what is your input voltage, and every time you must keep this amplitude at 3 volts peak to peak only. You should not change. All we need to monitor is this has to be constant, and this value, this amplitude, that is the output amplitude, will obviously keep on changing. You have to note that. Okay. And one more thing that you need to look here is all these networks that are behind this, they are made of amplifiers only. So it is not that you increase their amplitude. I mean, say for example, this particular lag compensator network where you can vary the gain here. When you are gaining, what happens is you will get all these particular output waveforms saturated, which means it will be clipped waveforms. Why they are getting clipped is because all those that are implemented behind this board, they are based on operational amplifiers, and these operational amplifiers, you know that they have a saturation level based on the biasing voltages. Right, operational amplifier, the biasing voltages will be from plus 15 or minus 15. So if you give your amplitude beyond plus 15 or minus 15, then they are going, your output is going to be saturated. But it is always better that we keep our amplitude less than close to 3 volts peak to peak, and we repeat the experiments for as I said, for the phase lag network.